Now let's work out an example of finding an integral of this form using residue theory. In our example, we'll find the integral from negative infinity to infinity of x squared over x to the fourth plus 1. First, let's check that the three conditions required are all satisfied. First of all, this is a rational function. It's a polynomial divided by another polynomial. The degree of the denominator is at least 2 bigger than the degree of the numerator. Here it's exactly 2 bigger than the degree of the numerator. And last of all, the function x to the fourth plus 1 is not equal to 0 for any real number. X to the fourth plus 1, in fact, is always positive when x is a real number. So what that means is, if we take this function and we replace the x's with z's, so we look at f of z equals z squared over z to the fourth plus 1, this integral will be the same as 2 pi I times the sum of the residues of f of z at z sub I, where I take the sum over all of the poles which are in the upper half plane. So first of all, we need to find where all the poles of f are, and then we need to find the residue at each of those poles. So the poles of f are going to be the places where the denominator is equal to 0. And in one of your early graded homework assignments, you found where all the zeros of z to the fourth plus 1 are. You might recall they were symmetrically placed on a unit circle around the origin. Let's call them z1, z2, z3, and z4, where z sub 1 is equal to e to the pi I over 4. Let's just write it as pi over 4i. z2 is e to the 3 pi over 4i. z3 is e to the 5 pi over 4i. And z4 is e to the 7 pi over 4i. Now, since I only care about the poles in the upper half plane, we're just focusing on z1 and z2. By the way, if we use Euler's formula, we can write this in the form a plus bi. z1 is going to be 1 over the square root of 2 plus 1 over the square root of 2i. And z2, over in the second quadrant, is negative 1 over root 2 plus 1 over root 2i. So we'll use whichever form is more convenient to us. So now we need to find the residue of f at each of these two poles. Now, since each one of these is a simple pole, we can find the residue of f at z sub 1, for example, by taking the limit as z goes to z sub 1 of z minus z sub 1 times f of z. Remember, that was a shortcut for calculating residues at simple poles. Now I'm going to try to kill 2 birds with 1 stone by just doing this for z sub I, where I could be either 1 or 2. I want to find the residue at z1 and at z2. So let me just put a z sub I in here, and then later on we'll look at those 2 cases separately. So this is the limit as z goes to z sub I of z minus z sub I multiplied by z squared over z to the fourth plus 1. Which is the limit as z goes to z sub I of z cubed minus z squared z sub I over z to the fourth plus 1. Now, since z sub I is a pole, we know that it makes the denominator equal to 0. And we also can see that if we plug in z right here, it makes the numerator equal to 0. So this is an indeterminate form, And we can apply L'Hopital's rule. So I can take the limit as z goes to z sub I of the derivative of the numerator over the derivative of the denominator. The derivative of the numerator is 3z squared minus 2z z sub I over 4z cubed. And now let's use direct substitution. I'm going to substitute z sub I in for z. I get 3z sub I squared minus 2z sub I squared over 4z sub I cubed. Which is z sub I squared over 4z sub I cubed, which is equal to 1 over 4 z sub I. So let me capture just the result of that and then figure out what the consequences are. So this is a long sentence. It says that the residue of the function at z sub I is equal to 1 over 4 z sub I. So now let's figure out what it is at z sub 1 and z sub 2 in particular. The residue of f at z sub 1 is going to be 1 over 4 e to the pi over 4 times I, because that's what z sub 1 is. That's the same as 1/4 e to the negative pi over 4 times I. And to evaluate this, you can use Euler's formula. In fact, I'll do that. This is 1/4 of cosine negative pi over 4 plus I times sine of negative pi over 4, which is 1/4 of 1 over root 2 minus 1 over root 2 times I. And for z2, the residue of f at z2 is 1 over 4 times, z sub 2 is e to the 3 pi over 4I. So this is 1/4 of e to the negative 3 pi over 4I. And once again, you can use Euler's formula. You can also think about it graphically. E to the negative 3 pi over 4 is the same as z3 here, which is negative 1 over square root of 2 minus 1 over square root of 2I. Cool. So capturing just the results, the residue at z1, if I distribute, is 1 over 4 square root of 2 minus 1 over 4 square root of 2 times I. And at z2 is negative 1 over 4 square root of 2 minus 1 over 4 square root of 2I. Now I think I can lose a lot of this stuff over here to the right. Now we're practically done. Look, this integral is equal to 2 pi I to the times the sum of these two residues. So we have 2 pi I times this one plus this one. Well, notice when I add these, I have 1 over 4 square root of 2 minus 1 over 4 square root of 2, and those cancel. And then I have minus 1 over 4 square root of 2I minus 1 over 4 square root of 2I. So I have 2 pi I times negative 2I over 4 square root of 2. Multiplying the 2 pi I into the numerator, I have negative 4 pi I squared over 4 square root of 2. I squared is negative 1, so that's 4 pi over 4 root 2, which is pi to the square root of 2. So the integral from negative infinity to infinity of x squared over x to the fourth plus 1 is equal to pi over the square root of 2.